Hello, everyone! In today's lesson, we'll start learning diverse strategies to evaluate limits analytically. That is, evaluating limits by relying on algebraic techniques instead of graphing or numerical approximations. At the start of your lesson, you had the pre-video activity, Evaluating Limits. If you haven't had a chance to work on it yet, pause the video to do that now. Let's work it out together. In the pre-video activity, we had to use limit laws and the special limits we learned in previous lessons to evaluate these limits. Let's take a look at the first one. Here are the limit laws we've learned so far. Using the sum and difference laws, we can break down this limit into the limits of each separate term. Then, we can use the constant multiple law to pull the 4 out of the second limit. Now, we can use our special limits to evaluate these 3 limits. Using this special limit, we know the limit as x approaches 3 of x squared is just 3 squared. Using this special limit, we know the limit as x approaches 3 of x is just 3, which, remember, is getting multiplied by 4. And this special limit tells us the limit as x approaches 3 of 5 is just 5. Simplifying this expression, we get a result of 2. Now on to the second limit. By the quotient law, we can break down the limit into the limit of the numerator over the limit of the denominator. Using the constant multiple and difference laws, we can pull out the 2 from the numerator and separate the denominator into 2 limits. Once again, we use our special limits, specifically these 3, to evaluate each of the limits. Now we just simplify, getting a final result of 6. Let's take a closer look at how we got to these results. In particular, look at the main calculation we ended up doing after we broke down with the limit laws. What do you notice? Didn't we actually just substitute the 3 in the x's? In other words, if we call this polynomial function f and this rational function g, then the value of our first limit was just f of 3, and the value of the second limit was just g of 3. So now you might be wondering, why didn't we just do that from the start? Why use the limit laws at all? We would have gotten to our results much faster. Well, by using the limit laws to evaluate limits of polynomial and rational functions like these, we were able to see how they are just basic operations on these special limits, which all involve just substituting in the value of a. So indeed, we can now say that, at least for polynomial and rational functions, the limit as x approaches a of f of x will in fact just be f of a, with one little important detail. A must be in the domain of f. We call this the direct substitution property. From now on, we can use this property instead of using the limit laws. Why does the direct substitution property make sense for polynomial and rational functions? Let's look at the graphs of the functions from the pre-video activity. Here's the quadratic function from the first limit, which is a parabola. What happens as we approach x equals 3? We simply approach the actual value it has at x equals 3. In other words, the limit as x approaches 3 of f of x is just f of 3, which is exactly what the direct substitution property says. Similarly, here's the graph of the rational function from the second limit. Once again, as we approach x equals 3, the graph goes directly toward the point at x equals 3. So the limit as x approaches 3 of g of x is just g of 3. This happens because polynomials and rational functions are continuous on their domains. In fact, the direct substitution property applies to all continuous functions, but we'll specifically be focusing on polynomial and rational functions for now. Let's practice applying direct substitution to evaluate some limits. First off, we have the limit of a polynomial. Since polynomial functions have a domain of all real numbers, -2 is in the domain of this cubic function, so we can use the direct substitution property and simply substitute -2 for x. After some simplifying, we find that the limit is 59. Pause the video and try out the next two limits. Now limit b. How can we know whether 4 is in the domain of this rational function? Well, we could first find the domain of the function and see what values make it undefined, but we can also just try to substitute the 4 in, and if 4 is not in the domain, we'll run into issues. However, simplifying this expression gives us a defined value of 1/3, which means 4 is in its domain, and 1/3 is in fact the value of the limit. Finally, limit c. Let's try to substitute in 3 for x and see what happens. It seems we get 0/0, which is, what? We know we cannot divide by 0, so does this limit simply not exist? Before we make any conclusions, let's backtrack a bit. Why did direct substitution not work here? Since 3 makes the denominator 0, we could have seen from the start 3 is not in the domain of the function, so the direct substitution property does not apply. That said, that doesn't mean this limit can't be found. At first glance, this fraction, 0/0, may seem like we've reached a dead end because we can't divide by 0. But 0/0 is actually a really interesting result. It's called an indeterminate form, and it doesn't mean we have to stop. It actually means that we need to investigate further because the limit may or may not exist. Let's see why. What do you notice about the function in this limit? Does anything stand out when you see x squared minus 9? From our algebra skills, we recognize this as a difference of squares, which factors into x plus 3 times x minus 3. We can now see x minus 3 is a common factor we can cancel, which leaves us with x plus 3. This means f of x behaves exactly like the function x plus 3 everywhere except at x equals 3, where it is undefined. From our work with rational functions, we know the graph of f will be the line x plus 3 with a hole at x equals 3. Does this give us insight about the limit we're trying to find? Does the function approach a specific value as x approaches 3? Yes! It approaches 6. However, our goal is to find the limit analytically without graphing. To do that, we need a function we can actually substitute x equals 3 into. What if we look at the related function g of x equals x plus 3? How are f and g related? Here's the graph of g of x. It's the same line. But now the point 3, 6 is included. This is an example of functions that agree at all but one point. F and g are not the same function because f has a hole at x equals 3 and g does not, but their limits as x approaches 3 are equal. Why? Because the limit does not care what happens at x equals 3, just what happens as we approach it. Therefore, the limit of f of x we've been wanting to evaluate analytically equals the limit of the simpler g of x, which is a limit we can evaluate with direct substitution. We replace x with 3 and get that the limit is 6, which confirms our earlier result. This example illustrates an important idea. If we have functions f and g that are equal everywhere except at x equals a, then their limits as x approaches a are equal, given these limits exist. This is exactly the scenario we had here. Since f and g were equal everywhere except at x equals 3, we were able to use g, a nice continuous linear function, to efficiently find the limit of f, which was undefined at 3. Let's apply this concept to a few examples. Here's a piecewise function f. Find the limit of f of x as x approaches 1. Pause the video and try it out. Function f is equal to x squared minus 4x everywhere except at x equals 1, and then at x equals 1, it's equal to negative 4. But we don't care about what happens at x equals 1. Therefore, since the function x squared minus 4x coincides with f everywhere except at x equals 1, the limit of f of x as x approaches 1 is equal to the limit of x squared minus 4x as x approaches 1, which we can evaluate using direct substitution. We find that the limit equals negative 3. Here's the graph of f, and here's the graph of x squared minus 4x. We can see that the functions agree at all but one point. So the limit of g of x as x approaches 1 will be the same as the limit of f of x as x approaches the same value. Let's look at another example. Find the limit as x approaches negative 7 of this rational function. How would you approach this one? We could try direct substitution and substitute negative 7 for x, and we end up with the indeterminate form 0 over 0. Remember, this doesn't tell us whether the limit exists or not. It just means we need to try something else. As before, let's see whether we can find a function that is equivalent to this one everywhere except at x equals negative 7. The last time this happened, we were able to find such a function by factoring and simplifying the rational expression. Pause the video and factor both the numerator and denominator of the function. We can pull out a GCF of 2 from the numerator and factor the denominator as x plus 7 times x minus 3. We got a common factor. We can cancel out x plus 7, which gives us the related function 2 over x minus 3 that's equivalent everywhere except at x equals negative 7, which was the problematic value that was giving us 0 over 0. Notice that when we do this simplification, we write that the limits are equal, not the actual functions. Not writing the limit symbol would be incorrect, as these two functions are not in fact equal, but their limits are. Now we can just use direct substitution to evaluate this limit, as this expression is defined when x equals negative 7. We get a limit of negative 1/5. Once you simplify a function and use direct substitution to find the limit, you can be confident in your answer and stop there. However, since this method is still new, let's check the graph to confirm that our result makes sense. Here's the graph of our original function, and here's the graph of the simpler function we used to get the limit. Both have the same limit as x approaches negative 7. Now try out this example. Pause the video now. Before doing any algebraic manipulation, like factoring, we can check whether we actually get an indeterminate form or whether direct substitution will do the trick by substituting 0 for x. Since we get the indeterminate form 0 over 0, let's remember we need to investigate further because the limit may or may not exist. Let's try some simplification and see what happens. Factoring numerator and denominator, we notice a common factor of x. Canceling 1x from the numerator and denominator, we get 3 times x plus 2 over negative 5x times x minus 2. Can we try direct substitution now? It doesn't seem like our simplifying helped much. We canceled a pair of x's, but there's still a factor of x in the denominator. If we try direct substitution now, we still get a 0 in the denominator. However, this time it's not the indeterminate form 0 over 0. It's 6 over 0. What does this mean? As you learned in previous lessons on rational functions, this means there is no hole in the graph. There's actually a vertical asymptote at x equals 0. What is the value of the limit then? Since the function doesn't approach anywhere specific, the limit does not exist. In fact, every time we try direct substitution and we get a non-zero constant over 0, we can be sure no amount of simplification will help. The function has a vertical asymptote and the limit does not exist. To wrap up this lesson, let's look at this final example that includes the various cases we've learned about. Before doing any factoring or simplifying of any sort, determine which limits can be evaluated without doing any algebraic manipulation. Pause the video now. Let's see what results we get from this limit when we attempt direct substitution. For limit a, when we substitute -4 in for x, we get absolutely no issues, and we directly get a value of 12 over 5 for the limit. For limit b, substituting in -4 yields 96 over 0. Since we got a non-zero constant over 0, there must be a vertical asymptote at x equals -4, and the limit does not exist. Finally, for limit c, substituting in -4 yields the indeterminate form 0 over 0. So in this case, we should attempt some algebraic manipulation. On your own, see whether you can evaluate the limit by first factoring and canceling out any common factors. Pause the video now. We factor the numerator and denominator, and notice we can in fact cancel out x plus 4, which then allows us to evaluate using direct substitution. We get that the limit equals 12 over 11. Today, we learned how to evaluate limits of polynomial and rational functions using the direct substitution property. We also learned that if a is not in the domain of a rational function, we can still try direct substitution to see whether it yields the indeterminate form 0 over 0, which means the limit may or may not exist, and we should try factoring and canceling out common factors, and then try direct substitution again. If direct substitution yields a non-zero constant over 0, then we can conclude the limit does not exist. Once you've finished your guided notes, complete the additional practice. After that, make sure to complete the online practice. See you next time!
Hey, hey.